So in this presentation, we have to talk about the relation between the differential scattering cross section and scattering amplitude. Usually in the process of scattering, if the incoming particles are far away from the scatterer, they may not realize any force. Suppose the particles are approaching closer to the scattering potential, they may be deviated to some extent. If you assume that the incoming beam is traveling along the z direction, if they approach closer to the scattering center, they may be scattered to some extent, and the scattered wave is treated as a spherical wave, whereas the incoming wave is a plane wave. So this is a diagram representing the entire process. This is incoming plane wave. The outgoing scattered wave is a spherical wave. As we pointed out earlier, at larger distance from the scattering potential, the effect of scattering potential on the incoming beam is negligible. So the incoming wave is plane wave, and the plane wave equation is a e power ik dot r. Here this k dot r is our kr cos theta. Using the formula a dot b equal to ab cos theta, we have changed this a e power ik dot r as a e power ikr cos theta. In spherical polar coordinates, z is equal to r cos theta. So psi a is written as a e power ikz. Here k is our propagation vector whose value is 2 pi by lambda. According to de Broglie, lambda is equal to h divided by mv. So this is 2 pi by h into mv. 2 pi by h is our 1 by h cross. Then mv is our momentum p. Here p is our mu into v. In our present case, instead of m, we have written mu. Mu is our reduced mass. Small m is the mass of the incoming particle and capital M is the mass of the target. Then reduced mass mu equal to small m capital M divided by small m plus capital M. When the incident beam reaches closer to the scattering potential, the particles get scattered on all directions. The angle between the incident and the scattered beam is called as scattering angle. Using the azimuthal angle, we may specify the direction of the scattered beam. The two directions together define the plane of scattering. Here the two direction means the incoming wave direction as well as the scattered direction define the plane of scattering. The azimuthal angle pi specifies the orientation of this plane with respect to some reference plane containing the z-axis. If you place the collector, that means the detector, far away from the scatterer and concentrate only on the asymptotic form of the scattered wave, the outgoing spherical wave is given by the formula psi s is a f of theta comma pi e power ikr by r. Here this f of theta comma pi is called our scattering amplitude. For spherically symmetric potential, f of theta comma pi is reduced as f of theta because in the case of spherically symmetric potential, there is no talk about pi. The value of pi is equal to 0. So that psi s is a f of theta e power ikr by r. Now the Schrodinger equation describing such type of scattering is given by the formula h psi equal to psi. Here this is our Hamiltonian operator, minus h cross squared by 2 mu del square plus v is our Hamiltonian operator. So h psi is equal to psi. Now we have to write the general solution for this equation for using our incoming wave and outgoing wave. The incoming wave is a plane wave, a e power ikz. Then the outgoing wave is a spherical wave, that is a f of theta e power ikr by r. So this is the solution for this equation 4. Here e power ikz and e power ikr by r are the two eigenstates of the particle. Now we have to arrive the relation between differential scattering cross section and scattering amplitude. For that, take our probability current density equation. We arrived at this equation 6 from our continuity equation. J of r comma t equal to h cross divided by 2 I mu into psi star grade psi minus psi into grade psi star is the equation representing the probability current density. We know the value of psi equal to a per I k z plus f of theta e per I k r by r. This is our psi. Then psi is simply modified as a e per I k z plus a into f of theta e per I k r by r. Take the complex conjugate of this equation, we can get psi star. Psi star is equal to a star e per minus I k z plus a star f star of theta e per minus I k r by r. Find out the grade psi, then differentiation of this. If you differentiate the first term, we can get e per I k z into I k then a. See here, if you differentiate e per I k z, we can get e per I k z into I k. So a is a constant. We kept this constant as such. Differentiation of e per I k z is e per I k z into I k. Now come to the second term. Here a and f of theta are constants maintained as such. Then e per I k r by r is differentiated using the u by v formula. This is square of the denominator r square. Then write down the term present in the denominator as numerator r. Then differentiate the term available in the numerator. Differentiation of this term is e per I k r into I k. So I k into e per I k r minus of the numerator term e per I k r. Then differentiate the denominator. If you differentiate r with respect to r, the value is 1. So this is the differentiation of e per I k r by r, this value. Now we may modify this term a I k e per I k z plus a into f of theta, this r and r square will be modified. So we can get I k e per I k r divided by r. Then minus of e per I k r divided by r square. Just I have separated this into two terms. R square. We can get I k e per I k r by r minus of e per I k r by r square. Then grade psi equal to a I k e per I k z plus a f of theta I k e per I k r by r minus of a into f of theta e per I k r by r square. In the same manner, we arrived at the value of grade psi star. Then this is the value of grade psi star. Now find out the value of psi star grade psi. This is the value of psi star. This is the value of grade psi. Now multiply the first term with this a star a, absolute square of a. Then this I k is written as such. Then e power minus I k z into e power plus I k z is e power 0 equal to 1. So multiplication of these two terms is absolute square of a into I k. Then allow this term to operate on the second term. See here, the first term is present in e power minus I k z, but this term is present in e power I k r. So multiplication of these two terms will provide 0 value because the overlapping term will not be taken on account. Overlapping term means one term is present in e power minus I k z and another one term is present in e power I k r. So this is called overlapping. So the result is 0. The same manner, e power minus I k z into e power I k r. If you multiply the first term with the last term, that value is also 0 because of the overlapping term. Now come to this second term. If you allow this second term to operate on this first, this is e power minus I k r, this is in e power I k z. The result is 0 because of the overlapping terms. Then the second term into second term, we can get some value. That is a star into a, absolute square of a. F star of theta into f of theta, absolute square of theta. Then write down this I k as such. E power minus I k r into e power plus I k r equal to e power 0. E power 0 is 1. Then 1 by r into r square. 1 by r square. So this into this. Then this into this is minus absolute square of a, absolute square of theta into 1 by r cube. This is the value of psi star grade psi. In the same manner, we can have the value of psi into grade psi star as this much. Now we have to substitute all the terms in the equation 6, that is our j of r comma t equal to h cross divided by 2 I mu into psi star grade psi minus psi into grade psi star. Now we have to subtract psi into grade psi star from the term psi star grade psi. Say this is our psi star grade psi, this is our psi into grade psi star. We have to subtract this term, this is right hand side, from this terms. Say absolute square of a ik minus of this term. So minus and minus plus. So 2 times ik absolute square of a. We are in the position to subtract the value of psi into grade psi star from psi star grade psi. So this term minus of this term, minus to minus plus. So 2 times ik into absolute square of a. Now come to the second term. Absolute square of a f theta square minus of this term. So minus and minus plus. So 2 times ik absolute square of a absolute square of theta into 1 by r square. Now consider this term minus of absolute square of a absolute square of f theta square 1 by r cube minus of this term, minus and minus plus. So these two terms are cancelled out. Therefore we can get j of r comma t as h cross divided by 2 I mu into 2 ik absolute square of a plus 2 ik absolute square of a absolute square of theta into 1 by r square. Then allow this term h cross divided by 2 I mu to operate on the first term. H cross k, 2i get cancelled, absolute square of a. H cross into k absolute square of a is the first term. Then h cross by 2 I mu into the second term will provide h cross k divided by mu absolute square of a absolute square of theta into 1 by r square. So the total current density j of r comma t is incident current density plus scattered current density. The value of incident current density is j equal to h cross k divided by mu into absolute square of a. This is our p divided by mu, but p equal to mu into v. So mu into v divided by mu into absolute square of a, which is equal to v into absolute square of a. Now come to our scattered current density term, that is equal to h cross k divided by mu absolute square of a absolute square of theta into 1 by r square. But h cross k is our p, but p is our mu v, so that we can get v into absolute square of a absolute square of theta into 1 by r square is our scattered current density. But the differential scattering cross section is probability current density of the scattered wave per unit solid angle divided by probability current density of the incident wave. Here JSC is v into absolute square of a absolute square of theta square into 1 by r square. Here this 1 by r square is the value of solid angle d omega. D omega equal to surface area divided by r square, but the surface area value is 1. Here 1 by r square is a solid angle subtended by the unit area of the detector at the scattering center. Therefore, in the numerator we have to substitute the value of JSC without 1 by r square. Therefore, v into absolute square of a into absolute square of theta is the probability current density of the scattered wave per unit solid angle divided by probability current density of the incident wave is v into absolute square of a. Therefore, we can get sigma theta equal to absolute square of f of theta, which means that the differential scattering cross section is equal to square of the scattering amplitude, absolute square of the scattering amplitude. We know that the scattering amplitude has a dimension of length. Therefore, the differential scattering cross section has the dimension of length square. In order to evaluate the value of scattering amplitude, we have to follow two techniques. One is Born approximation and another one is partial wave analysis. With the help of these two techniques, you can find the value of f of theta. Thank you.